Martin Rahm. Martin got his Master of Science degree in Chemistry and Chemical Engineering in 2006 at the Department of Chemistry of the Royal Institute of Technology in Sweden. Then in 2011, he received the PhD in Physical Chemistry from the same institution under the supervision of Tore Brink and Eva Malmström. And then he moved to the US for 2 postdoctoral experiences. The first one from 2011 to 2014 at the University of Southern California, where he worked on the modeling and synthesis of high energy density materials under the supervision of Carl Christ. And the second one from 2014 to 2017 at Cornell University, where he worked with the Nobel laureate Roald Hoffmann and with Neil Ashcroft. Then in 2017, moved back to Sweden, where he was hired initially as assistant professor at the Department of Chemistry and Chemical Engineering of the Chalmers University of Technology in Gothenburg. And there, since 2021, he has been a tenured associate professor in theoretical chemistry. During his very young career, Martin got several awards and recognitions. For example, in 2013, he received the Arthur Adamson Postdoctoral Recognition Award for scholarly excellence and innovative postdoctoral research at the University of Southern California and the department from the Department of Chemistry in particular. Always in 2013, he also received the Dr. Bernard Duda Young Scientist Award for the synthesis of nitrile cyanide from the International Pyrotechnic Society. And also in 2013, he was also selected for the 63rd Lindau Nobel Laureate Meeting in Chemistry. He also got several postdoctoral fellowships and travel grants. Among his different research interests, Martin recently also moved to the domain of quantum computing. And today his talk will be about this research topic, and I guess he will also try to find a connection between the world of quantum computing and quantum crystallography. So I'm very interested to listen to your talk. So now the stage is yours.
Thank you so much for the kind introduction and for the invitation. I'm very happy to interact with the community, even if it's only in 2 dimensions. So, as Alessandro said, I am from Sweden. So this is where Chalmers is, for those that don't know. And this is how the city and the university looks on a fair day. You are an excellent community, everyone listening. So if anyone is nearby, I'd be almost certain to be happy to host you. So let me know if you're nearby. We are doing different things in my group, all theoretical chemistry. But in brief, we work on chemical bonding a lot. Why do we work on chemical bonding? Is illustrated here by, this is the output if you ask GPT-4 to draw a benzene molecule. It can't. Anyway, jokes aside, that's what we do. We also apply quantum chemistry to problems in astrochemistry and astrobiology, studying more extreme conditions that are hard to do experiments on. And of late, we have begun studying quantum computation of chemistry. And that is what I will mostly be talking about today, coupled to some chemical bonding, you could say. So since quantum computation is not really this field, I'm going to spend some time on some introductory topics that I hope will be appreciated. And I'll also mention that, mostly for students and postdocs, that there's a rather large, with Swedish measures at least, center or effort in Sweden called the Wallenberg Center for Quantum Technology, or VACT, where the objective is to build up competence in quantum technology and also build quantum computers. And this is more than 100 people. Most of them are at Chalmers. More than 100 people working on this topic, which is one of the largest collections of people on quantum technology in academia in Europe, actually. And several other universities are involved with this as well. It's a 12-year project. We're about halfway, and most people in this effort are physicists. Many are involved with the hardware and some on algorithms. And my group is one of the few, the only, I think, actually, quantum chemists trying to use these machines. So for those that are interested, there are usually several opportunities for PhD positions and postdoc positions, and you can search for that. Funding for what I will be talking about today comes from VACT mainly, but also from the quantum flagship of the European Union. One of the projects there called Open SuperQ, and its successor Open SuperQ Plus. I really wish they had called it Open Super Duper Q, but anyway, we also have AstraZeneca that have supported us with one PhD student that was involved in this project. So most of what I will be talking about today, at least on the subject matter, is captured in this rather recent paper that I've written it. We have written it in a way that I'm fairly certain would be appreciated by people outside the community. So you can go to that as a reference point if I make no sense at some point, or if I can't answer your questions. And it was a very nice collaboration between the people in my group, who are Morten, Werner, and Falgun, and quantum hardware people, if you like, which are the remaining authors here, aside from myself. Yes, there we go. So the point of this paper is to, and this talk, I guess, is to highlight the connection between the electron density, which this community, quantum crystallography cares a lot about, and quantum computation. So first, a little bit about, for the 1.5 person in the audience that might not know why we care about the electron density, I'll first defer to authority and mention Walter Kohn, who won the Nobel Prize for the development of DFT. Now, it was actually Dylan Yatilaka that reminded me of this some time ago, that he pointed out in his Nobel lecture at one point that the wave function is not really a legitimate concept for very large systems. It just becomes too complicated to consider for large systems. And that's a very good motivation then to develop quantum methods based on the density. So, of course, the electron density is a much simpler beast to handle than the higher dimensional, rather complicated wave functions. And he later proved, together with Honenberg, that the energy is a unique functional of this density for ground state systems. And the resulting density functional theory is really, it's hard to put into words really how extremely revolutionary that has been for chemistry, physics, material science, and so on. It's so successful and simple, in fact. Well, simple might be provocative, but it's so successful that it's to date not really suitable for implementation on quantum hardware. There could be ways to do that, but I'll be happy to talk about it. But anyway, that's one way to think about the density, why it's important. Another one is, of course, that it is observable, at least indirectly. So here I'm showing you some data from good Danish people, Bo Iversen's group from about a decade ago, just to illustrate how this is the second derivative of the density, the Laplacian, in potassium sulfate, where diffraction data are fitted to some multipolar model. And why am I showing this? Well, they did. Same good Danes showed here an example of how you can use it to compare to theory. So the black curve here is again the Laplacian, but that's good DFT, and the red curve is their experimentally determined electron density, plotted along some bond axis between sulfur and oxygen. So we will return to why this is important. Other things, of course, also very well known in this community, is that you can use the framework pioneered by Bader and others from the 60s and onwards to do topological analysis of densities. This is just an example of how that could look like. If you look at the gradient of the density, you can use it to define atoms inside molecules. And then once you have atoms, you can attribute them with properties such as charge. In this case of diborane from a few years ago, you know, a chemist would be happy to know that hydrogen is hydritic and boron is positively charged, for example. So the density allows for allows for frameworks for analyzing electronic structure, which we care about. The point of this talk is, however, to introduce or just at least start a discussion on the use of densities as benchmarks for quantum computation that may prove especially important in the future. And I will get to why, but that's the new utility that we hope for the density. Now, I'll speak a bit about why one might want a quantum computer, and I fully realize that this is an extremely hyped field of research. There's a lot of money flowing into it. There's a lot of media attention, and popular science usually gets it wrong. There's a lot of press releases and so on. One of the key reasons and one of the potential future killer applications of a quantum computer is the accurate solving electronic structure problems, doing quantum chemistry. Now, the electronic structure problems most of you familiar with, the Schrödinger equation. So I'll stay with that for just a brief bit here. One way of looking at it is to think of what are all the things you have to account for in an electronic system. You have to consider the kinetic energy of all of the electrons. You have to consider the kinetic energy of the nuclei, electron-nuclear attraction, electron-electron repulsion, which is really the tricky part, and then nuclear-nuclear repulsion. Now, I put this up here in this particular form because Neil Ashcroft once told me that he was a student in Cambridge in 1962 when Dirac was there to lecture, and then he wrote down this exact equation or this exact expression for the Hamiltonian, and then he exclaimed that this explains all of chemistry. And everyone laughed, of course, because they were physicists. I think of this quote sometimes because it's a motivation for those working on chemical bonding, because this, of course, it's a joke of his. It doesn't really explain much, but it describes physics. There's a longer quote to the same effect attributed to him earlier, but at this point he said this shortly. Okay, so in what follows, we will actually, or what one typically does is you simplify this using the Born-Oppenheimer approximation. So you assume stationary nuclei. That means that you can essentially ignore this term of the kinetic energy of the nuclei, and this last term, nuclear repulsion, is a constant, and you are left with the electronic Hamiltonian. That in most textbooks looks like this, but for what follows, we will consider in second quantization. Second quantization is a useful formulation of this in quantum computation. And this is exactly the same thing, just for those unfamiliar. These A and A daggers here, they correspond to creation and annihilation operators. You can think of them as populating or depopulating an orbital or a configuration. And these, normal orbitals. Whereas these Hij and IJKL here, they are 1 electron integrals and 2 electron integrals. And in later what follows, when I'll talk about quantum computation, these integrals we will solve on a conventional computer, whereas it is, roughly speaking, these population of orbitals, the creation and annihilation operators, that we will encode on a quantum device. So there's a hybrid approach to this. So still with conventional quantum chemistry, right? The first trial state that you'd start with typically would be the Hartree-Fock state, which is a single determinant, a bunch of eigenfunctions that we call orbitals that are occupied in some manner. Now, the way towards the exact solution, if you have a really strongly correlated, difficult problem, the way to go towards that exact solution rigorously is to make this more complicated, rather, but include more and more virtual excitations within this space of orbitals. You do that by creating new configurations, new slated determinants, and this is where these operators come in. And if you do this with every possible permutation of electrons over orbitals, you have the full CI, the full configuration interaction wave function, and a near exact solution. The problem of this is, as illustrated by this figure, it scales exponentially. So it scales exponentially with system size. Exponentially is very bad. It's really the worst kind of scaling you can imagine. It also means that the memory needed to solve this wave function scales exponentially. So to illustrate that, we can look at just some very small molecules here that are, really small. 2 orbitals, sigma and sigma star, and 2 electrons in H2. You need 4 configurations, or if you don't do any tricks. And then you go up to about 2 billion for F2. And if you move this up to, say, 25, 30, 40 electrons, then all of a sudden you hit this really exponential wall where soon you need more configurations stored than there's atoms in the universe. And this is really the problem of there's of course many conventional tricks you can do. You can omit, you can limit your active space and do things. But if you have a large, strongly correlated system, it can't be done currently. So this is exponentially scaling, and this leads me then into why we want a quantum computer. I think everyone on the planet these days know this comparison, but on a conventional machine, you store data binary as 0 or 1s. On a quantum device, you work with qubits that can be in that can also be in 2 states, for example, 0 or 1, but they operate, or you can think of them as a sphere called a block sphere, where you can actually create a state that points anywhere on this surface. So you can, for example, create a perfect superposition of 1 and 2, or any other, including the phases associated with rotating around the sphere as well. This in itself doesn't give any advantage, and that's only 1 qubit. But if you have 2, if you combine 2 qubits, then you can all of a sudden create a superposition of 4 states. So 0, 0, 1, 0, or 0, 1, and 1, 1. I have omitted here some coefficients in front of this as well. Then if we go to 3 qubits, you have 3 qubits that you can combine, then we have a superposition of 8 states. So you see where this is going. We can store quantum states that are exponentially smaller, with exponentially smaller resources. So n qubits can encode 2 to the power of n computational basis states in principle, and this is why quantum memory is very large. And for our purposes here, you can think of qubits as scaling linearly with number of orbitals in your active space. Okay, so that's the motivation. I'll try not to bullshit anyone here. So there's a long way. No one really knows how long the way is for actual advantage of quantum devices and computation of chemistry with quantum devices. So from the early days when the idea of quantum computers were invented, we're currently in what's typically called the noisy intermediate scale quantum era, or NISQ era. That means that we have tens to hundreds of qubits. On state-of-the-art IBM hardware would have a few hundred qubits, and they would be terribly noisy. Okay, so this is not a great place to be. The current quantum hardware is really tiny, and noise is bad. Right? So noise meaning that the programs you run sometimes gives you rubbish, and the quantum states that you create disappear. Furthermore, there's in this era that we currently have, NISQ era, there's actually no useful algorithm that has been demonstrated. So there's plenty of algorithms, programs that people are using, us included, but there's no mathematical or empirical proof of any advantage whatsoever. There is, however, in the future, currently there's mathematical proof for certain few number of algorithms for specific problems if one has thousands of qubits or millions of qubits that are fault tolerant, near perfect. So it's an open question if in the near term we have utility or not. And we can talk much more about this in the question session if anyone is interested. So what is the current state of the art then for quantum chemistry? Maybe not the state of the art, but at least the most commonly used variational algorithm for chemistry is the VQE, the variational quantum eigensolver. I'll talk briefly about it. Something like this is a hybrid approach where you combine the resources of a conventional machine, computer, and some quantum hardware. On the left side here, you start out with your electronic Hamiltonian that I began speaking about, and then you encode that problem into a qubit Hamiltonian. You map them to qubits, and this can be done in different ways. In the simplest, most straightforward way, you can think of it as we are encoding the occupations of orbitals or configurations. Then we have some quantum circuit ansatz here that entangles and does things to these qubits, and then afterwards we read out the values of these qubits, where they are statistically. So you do these readouts many times, and then you reconstitute the expectation value for the Hamiltonian. So parts of the Hamiltonian will have been computed, part of the expectation value will have been computed conventionally, and part of it will be from this quantum circuit. And then you put all of this into a classical optimizer, conventional optimizer. And the optimizer's job is to optimize the parameters. You can think of them as the angles that determine where on this block sphere the state is. The job of the optimizer is to change the parameters so to minimize the energy. And herein lies also the problems of this and why I think that there's no chance, if I were to bet, that there's not going to be an advantage from such type of algorithms, because this classic, even though in principle we have an exponentially large quantum memory here, if you have a large quantum device, here you have to find the ground state using a conventional optimizer, and the parameter space is still scaling very badly. Nonetheless, this is we learn a lot from playing with these algorithms. They're still not great, but you learn a lot from them, dealing with noise, the encoding problem, and so on. There's a lot of progress. It's a hideous amount of progress, actually, and there's very good reviews to read for those interested in this. Now, I cannot really tell you what the algorithm of the future will look like. What is the most promising one that could actually show advantage? The only thing I can tell you with some certainty is that it will have a very long acronym. Okay, so we started with the VQE like about a decade ago, and currently in my group we are working with the trans-correlated adaptive variational quantum imaginary time evolution. So that's quite the mouthful, and by the time this is actually useful, we'll have to add way more letters to it. So why am I telling you this? Well, these kinds of calculations are done on small molecules with limited basis sets typically and active spaces, sufficiently so that you can compute them exactly or near exactly with conventional quantum chemistry. And that is also how you benchmark these calculations, see how typically bad they are. You need the total electronic energy. Now, hopefully, this will become impossible in the near future, because if we have sufficiently good hard quantum devices of say 40-50 qubits, you can in principle do calculations that are impossible to replicate on a normal machine. And then there's a really, I mean, this is rather concerning how one benchmarks quantum output in general. I mean, there's many other problems that you could use for that you could apply a quantum computer to, but in quantum chemistry, maybe this will be rather problematic, and this is why the density comes back. Okay. In this paper and in this talk, I'm going to advocate for the use of the electron density obtained experimentally as a benchmark of future calculations. So what we've done here is actually the first calculation of electron densities using quantum hardware, but they are really, really small. They're only proof of principle. There's precisely zero advantage in doing this. It's a proof of concept piece. So I'll tell you now how we go about doing this in a way that I think will stand in 10 years and 20 years. So the generality of how you can compute an electron density, you can express it in the second quantization formalism. So you can express the electron density as follows. These phi's here, they are spin orbitals, normal spin orbitals, where the p's and the q's and the sigmas here are spatial and spin indices. And in what we do, these are conventionally evaluated, classically computed. And then this dpq here, these are entries of the one electron reduced density matrix. And you can think of this as a weighing factor, if you will, that corresponds to the occupation of these spin orbitals. So step one in doing this in a quantum computer is first to converge a wave function, find the state of interest. And what we have done is use this VQE. So in our case, it's a minimization of these quantum circuit parameters. You minimize this expression that is normalized with respect to these quantum circuit parameters. But in principle, in the future, you could use some other algorithm to find a quantum state. And therein lies the difficulty. So after you have that, you would measure these entries you would measure the 1 RDM. And if you do this, the first part smartly, you already have all of these, or you can refine them afterwards. This is not a bottleneck, so this scales about as the square of the size of the system. So it's no problem. Once you have them, you can then reconstitute the density using this hybrid approach. And once you have it, you can do the regular, you can apply the regular QTEM machinery to do a topological analysis. And then ideally compare this then to some high accurate benchmark or fidelity witness that could either be computational or possibly experimental. So I'll show you some rough results here. Down on the bottom here, we have 1 RDM results, or rather it's the error of the 1 RDM entries with respect to the exact solution that we have access to. The H2 and the lithium hydride data are from hardware. This is Chalmers data, this is IBM data. The lithium 2 is an HCN, or simulated on large computers using realistic quantum hardware noise, or simulated noise. The units of these entries are electrons. So by how many electrons are you wrong? And you can think of the diagonal here as the occupation. This is the error in the occupation, but the diagonal of the 1 RDM are the occupation of the different configurations or orbitals. And you see that this is rather bad, right? So you have large fractions of electrons that are wrong. Okay, the off-diagonal terms a little bit less intuitive to think about, but they are also important, and they play a role. So one thing that we always have to deal with in this current NISQ era is to measure something that's rather noisy and then try to make sense of it. And then you have to some degree, do noise mitigation. There's many ways of doing this. In this particular case, we tried out something that's rather straightforward. One is to enforce transpose symmetry of these matrices. So these are Hermitian matrices. So the off-diagonal terms should be equal, but they're not due to noise. So we can rescale these entries so that they are equal. So as a physics rescaling. Another one is to normalize the diagonal, so you actually sum them, so that the sum is the correct number of electrons. And I emphasize that there are many other, also very more elegant ways of doing this with post-selection based on the correct quantum numbers and so on. This was just to see if we can improve on the density. So here's, for example, the number of electrons then in our test set of molecules, where we better have 4 electrons in lithium hydride. But when we run a calculation, we are missing some electrons. Okay, so this is what happens when you have noise. The statistical deviation here is our answer lies within this certainty, and the certainty is due to the number of samples, the number of shots that you queried the quantum processor with. It's quantum mechanics, so you have to do millions of, or tens of thousands at least, samples. We can mitigate for this so we have the right number of electrons. Okay. Another nice, I think, way as a chemist, I wanted to do a little chemical reality check on these densities. So we can then go ahead and do a Q-time analysis, and you know, we better come out with a hydritic hydrogen, for example, and we do. This is the perfect answer, and this is the noisy answer. We're sort of losing electrons on the hydrogen. Reasons for these I can't go into, but anyway, we can mitigate for this. The same simple approach I showed you works for lithium hydride, but it doesn't really work for these other cases for reasons we understand. It deals with the limits of the basis set and the active space, actually. Anyway, this is still early days, right? So this is another way of looking at this, the density as a metric for quality by difference maps that many in the community are familiar with. So this just shows you how off you are in different regions where you have too many electrons, where you have too few. Red is too many, blue is too few. And top left here we have difference between noisy and noise-free in these 4 different cases. In the middle row here we have our mitigated best estimate of the density compared to noise-free. There's not too much difference. And in the bottom row here we have our best effort compared to a really accurate conventional coupled cluster calculation with a large basis set, so near exact reference. Which is just really emphasize how bad it is currently. And one could, of course, improve this slightly, but there's the takeaway here is that there's this is even a visual way of benchmarking. And I think I'll end here, basically. I want this to be a rallying cry for quantum crystallography. Maybe you can use it as an additional motivator to pursue really high accurate experimental estimates. I'm not personally one to go into a synchrotron to do these measurements, so to the degree to which this can be improved is up to you to know better. But I think the density will become important for this purpose if it can be resolved well enough. And I look forward to hearing what you think and for a little discussion. Thank you.
Thank you very much, Martin, for the very interesting talk. Now the session is open for questions. You can, as I reminded you, can write your questions in the chat. I will read them, and then Martin will answer to them. I can start. I can answer a couple of questions to Martin. I read your paper. So I know that you didn't want to show some specific details. For example, I read that you, if I'm not wrong, you used an hardware efficient wave function ansatz, right, for these calculations?
Come again, what kind of ansatz?
You used an hardware efficient ansatz, right?
Yes, that's the correct.
So my question is the following one. So you use the hardware efficient ansatz, not a chemically inspired wave function ansatz. So this means that you obtain a wave, through the variational quantum eigensolver, you obtain a possible wave function, right? And of course, noise affected this wave function you obtained. Then, if I understood correctly, you use this wave function to perform the measurements of the density matrix elements, right?
Yes.
And in this measurement, you introduce noise a second time. So my question is it possible to, if you use a chemically inspired wave function ansatz, for example, a unitary coupled cluster, and you use that directly then the amplitudes, you can compute the density matrix elements directly in a traditional way, and you introduce the noise only once?
Actually, we do not measure them again, so the entries. So you get those entries as the VQE cycle goes on.
Okay.
Yeah.
Okay.
So, but in principle, if one were to give you like this is the parameters for the ground state, that's why I said then you could measure them rather cheaply. On the hardware efficient ansatz issue, it's really I mean, yeah, they're more efficient because they're small, but there's no physics there.
Yes,
people use them. I'm rather frustrated by this, so it's good you asked. These are just, they're circuits which entangle qubits that may have some physical interpretation. You could interpret them as occupancies, maybe, if you do the conversion correctly. But then the ansatz itself could be just random entanglements, more or less, by some depth. And the only reason really why people use them is because you have to have something really shallow. So if you use a chemically inspired ansatz like a unitary couple cluster, you end up with too large. It's completely impossibly too large to run on current hardware.
But don't you think that maybe with the chemical inspired wave function ansatz, you obtain better results for density as well?
You would also get rid of, but you can't run them currently because you'd have to have thousands of gates instead of like tens of gates.
Yeah, the depth of the circuit is.
Yeah. So it's only like the harsh reality that hits you in the face once you go from like fancy algorithm to, okay, let's try to make this, and then the noise hits you, and then you have to deal with that somehow. So unfortunately, currently hardware efficient is necessary, and they're not efficient; they're just short. Yeah.
Okay.
Yeah.
And the second question I have is about the let's say the mitigation you used, so the constraint. So one is about the number of electrons, the other one is about the symmetry of the density matrix, right?
Yeah.
So it's not another way, because if you impose these constraints, is it not? Maybe I'm wrong, but it's not as let's say artificially removing the noise effect. So you are showing basically that your results are better than what they actually are.
Indeed. So previously we have worked on other more chemically inspired error mitigation strategies that focuses on the energy, the total energy, right? And that's the focus of most error mitigation schemes. In this one, since we just started looking at it, 1RDMs, you're completely right. It's just a rescaling of rather bad data, and it has nasty consequences, and we tried it out. So we're currently working on what's called post-selection, where you immediately following measurement, check if this is corresponding to a physically reasonable state, and if it's not, we throw it away. Then you have to throw away a lot. Okay. And then that helps a lot. So by all means, don't use that particular kind of error mitigation.
Okay.
Yeah.
I see there is another question. So it is from Marcin Ziemniak. I mean, there was also a remark that Thomas and Fermi used the statistical model in 1927 to approximate distribution of electrons in an atom. The question is so thank you for the lecture. Is it necessary to use full quantum computers for computational problem in chemistry instead of quantum simulators such as D-wave quantum computers, which recently were used for Ising model calculations?
Yeah, so there are there's several different kinds of quantum computers. And the D-wave is forgotten what it's called now, but it's sort of like a quantum annealer. It works on different principles. Also, in that case, there's actually no evidence, even though I'm sure that company would disagree, of actual advantage. So I'm not an expert in how D-wave style quantum annealers work, but in the work, most other, like Google, IBM, Chalmers and others, work on superconducting qubits, which are much more limited in the number of qubits that you have, and they're of higher quality than that type of systems. So the question is if it's necessary. Well, I mean, what works is still an open question. So there's no advantage demonstrated by anyone, I would argue. There's plenty of promise. I haven't read that particular preprint though.
Another question from Peter. He asked in how big molecules can charge density actually be measured instead of computed? Maybe.
Well, that would be an experimental question if you mean measured as in diffraction. So I guess fantastically large unit cells have been made for, I don't know, what is it, potassium or something. But that's really what I would like to hear from you guys, if the limits. And what do you think, Alessandro? Is this a?
I'm a theoretician. I like. I leave Paulina to answer.
Because you can totally shoot me down. I'd be interested to know if this is.
So it's actually a question to what accuracy you want to measure it, because the accuracy we considered good enough for quantum crystallography descript refinement, let's say like that, or charge density refinement, where there are a few data sets for proteins reaching subatomic resolution, and for these data sets, the multipolar model was used to refine electron density distribution. But that's the good question. If this is accuracy already good enough to challenge quantum computing at the moment?
I would probably, so like enzymes and things like that, biological systems. I mean, I guess the largest problem would be when you have strong correlations. So like some superconductor or some really well-defined material, but that is electronically very challenged, that you could get really high quality diffraction data for. That DFT would just get wrong or just sort of right. Was the kind of thing I was thinking about, not these huge biological systems, because then there's typically a small part of it that might be very tricky to do.
Yeah, that's true. So for small molecules or inorganic crystals, it's more often possible to get super high resolution data and challenge current quantum chemical calculations and done on standard computers.
Yeah.
But it's not that for every system it is possible.
No.
Yeah.
Well, you probably have a few more years to refine, because very few people are. I mean, there's advanced. Most quantum computation is done on molecular systems, like I was showing you, not as much on extended systems yet. So, and it's unknown when the breakthrough will happen.
Yeah, and with our second speaker, there is also a possibility now to measure electrostatic potential, maybe not at the level of accuracy we wish to have it at the moment, but I hope that in the future it also will present very high accurate results. How about using electrostatic potential as a benchmark? I knew that there is no theory behind, well, but sometimes, it is more sensitive to charge distribution, or at least it should be more sensitive.
So this is a question to me, right? So our specialty, as you will see in a minute, is ultra-fast dynamics. And of course, we measure also charge densities. So I'm not very aware of how good you can measure in the static case. So the question to Martin and all of you is more like, at what point of big complex molecule is actually the computation, classical computation and new quantum computation actually becoming relevant? So I don't know the answer myself.
So I guess it's not only about the size, it's also about the different kind of effects which are experimentally observed and could not be explained by current theories, like especially this dispersion interactions or van der Waals interactions, which are very difficult. The interactions based on electron correlation, for example, which are still difficult to be described by theory, but there are examples that you can measure these effects accurately enough using quantum crystallography approaches. So it's not only always about the size of the system.
There is a remark by Hans-Beat Burgi. So he wrote, I'm surprised that you consider experimental density as a reference. Present experiments are highly developed with respect to modeling structure factors. However, there are only very crude physical models for processing diffraction data into structure factors. We know little about the limitations during data processing, Bragg versus diffuse scattering, etc.
Mm-hmm. Yeah, it is meant as a challenge and a question, really. But the point being that any kind of experimental data, no matter what it is, will become important, because you cannot go into a lab and measure a total energy, right? So that's the basic problem. You have to go into the lab and measure something else of your system that you have quantum mechanically calculated to verify it, be it densities or something else. Density is very rich in features, so hence the idea. But I don't know if it's feasible. You know better, certainly.
I have another curiosity, but although it is not strictly related to the talks, you mentioned about, I didn't read the paper, so I don't know, what your new algorithm, transcorrelated, so can it be a real advantage compared to the VQE, do you think? So what are the, in few words, what are the advantages?
Yeah, so it just got accepted in Faraday, in a Faraday contribution, actually, but it's on archive if anyone wants to look. The advantage is, in brief, that it provides very accurate energies near the complete basis set limit, despite running with a small basis set using a trick called transcorrelation. So it's we hijacked a conventional approach, and there's some possible advantages in the optimization also problem in the future.
You mean an optimization problem? You mean
the optimization of finding the ground state? So one can do
in the classical part. You know?
Yeah, so one could in principle do quantum imaginary time evolution towards the ground state.
So it is done. Is it done in a, not in a classical way as in the variational quantum eigensolver, but it is done quantum mechanically. Do you mean?
Yes, but there's downside of this approach currently as well, in that one only works with the right eigenvector, for example. So you can't really get properties, for example. You couldn't get densities currently from that approach.
Okay.
But it's a bit of a head scratcher, and it's a lot of things in there. I'd be happy to talk more if you check it out. And this is a highly collaborative effort also. Several, we've sort of hijacked this method from several other groups that have developed parts of it.
I will have a
conventional calculation.
Okay. Are there any questions?
So if you start out from scratch, you should probably start with the VQE. There's lots to learn there.
I know, sure.
Yeah.
Yeah. And I mean, yeah, maybe another question. Which kind of encoding do you use? If I'm not wrong, you use two kind of encodings when I read your paper for this work about electron densities, right? And if I remember correctly, there are also, if you use the parity encoding, you improve the results with respect to the Jordan-Wigner encoding.
Yeah, the parity can make slightly shorter circuits. You can cut off a few, and you can cut off a few qubits for smaller systems, but the Jordan-Wigner is nicer for chemists because it has this one-to-one mapping, occupation, orbital occupation, qubit. So no, it was parity, or possibly as well as another one as well.
Oh, it's not Bravik-Kitaev.
It's probably Bravik-Kitaev and parity. There's 4 different calculations in there, so I got no Jordan-Wigner.
Okay, if there are no more questions, I would like to thank again Martin for the talk and for the question and answer session.